So, okay, guys. We're always on the same topic because it's going to be a long topic. And I finally got myself to add the beginning of the pricing part. And most of it I've got. And then we can move on afterwards to how to do optimal behavior and get the Euler-Lagrange equation. Anyway, so I've divided it now in two sections. So this is all about the trade. Remember, this was the picture. These people are just trading. All we're talking about is the movement of the goods. All right. And when I say movement of the goods, keep in mind that money is also a good. All right. Credit money, whatever you feel like defining money is a good. It's something that's flowing. Okay. It's distinct from value. Now I know that economists like to, think of money as a way of measuring value, but you could have used bananas too, or seashells, and people do, okay? So I really want to see money flows as a separate thing, okay? It's just purely physical. So don't confuse the two in your models, all right? All right, so we don't want to do any of those things anymore. We went through it, and we did this, and then we did a bunch of other things. And then we went to this rigid body motion. And for the rigid, there are three types of capital theories. Maybe that's important just to emphasize. Okay, so here we have submanifolds. For us, these are, we can view them as holonomic constraints. So we have a space of two variables. This is a sort of form of capital. This is a product or a yield or a return on that capital, okay? These are these amortizing loans, remember, or cows that are dying. Amortized and dying is the same thing, but it could be money that's being paid off as a loan. These is your typical classical land, and it doesn't change, but it yields its crop. And these are the compounding things, like when you have exponential growth models, okay? All right. And all of them we view as rotations. That's important. For all of them, the radius here, we measure the radius a little bit differently. Okay. Here it's a good old Euclidean distance. Here it's a special distance that is just equal to whatever this coordinate, the cosine. At 0, it always stays the same. And here you have a hyperbolic distance, a Minkowski distance, it's always also called. Okay, so just a different notion of distance. So get that right, and then all your equations can work out, and you can use the exponential map, which is a discount, the regular discounting formula for all these things. Okay, and these things are generally known as groups of Lie groups because you can think of the amortizing as an action. So you amortize. Okay, so you go a step further. All right, it's like a rotation. Okay. Here you shear. And all of these have an exponential function where you can say, well, all right, I know what happens at very locally. All right, I'm going like this or like that, right? And then if I know that, so that is the element of the Lie algebra, I can exponentiate it out, and then I move into the group itself, So then I get a rotation if I use I squared is 1. I get a shear if I use some I squared, I call it epsilon is 0, or I get this if I take these. This is just a way to represent the groups, okay? And it's a way, I did it this way because you're so familiar with these results, but you could have done with a matrix. You could have done it totally abstractly. There's other ways to represent it, all right? Either way, whatever representation you choose, you can choose the arc length to, as the parameter, as the coordinate, all right? Okay. Then we expanded on this idea. So we did all kinds of stuff, all kinds of examples, production possibility frontiers. We had this thing, all right? And then we went one step further, and we're going to look at a firm, all right? So you can have, we look at it as a rigid body. So here we are. So we not only have an asset, but we complement it with a liability, all right? And we look how these things move together, right? So what does the asset do? It gives us yield, and the liability is the opposite. We have to pay for it, right? So these are the benefits, and these are the costs that are associated with it. Okay, this is like in a rotation. So this is a rotation. This is the same. This is the standard rotation, and this is also a rotation, right? So it rotates like this. These distances always remain the same. That's your initial capital, all right? Huh? And we calculate this initial capital using the usual formula from complex algebra, all right? Again, you can do all this abstractly, but this helps, okay? Especially this, because this you all know, all right? And then we said, all right, if you're just in business, you can also like move the, the fulcrum of your business, okay? So now you can do a rotation, or a shear in this case, huh? And you can move along this k dimension, along this x dimension. So we discussed how this could be different perspectives. So when you feel you're not moving, that's when you're in the corporation itself, managing the corporation, all right? So you're not receiving the net earnings. You're not injecting the capital. You're just running the business, okay? So you're harvesting and you're paying out whatever your debtors are, okay? Okay? But the investor, he has a very different thing. He doesn't really concern himself with this. He's concerning himself how much your center of mass is moving, okay? And if you put these things together, and they have this funny thing called the semi-direct product, huh? But it's not so important. Well, it is important, but you just know how to handle this, right? You know, you rotate and you shift. It's a little different than shifting and then rotating. You get somewhere else. I think in the plane maybe it will get a little simpler, but it doesn't matter. All right? So that allows us, this is what we normally call as the spatial frame or the global frame, all right? And this is what we would call the body frame. So you attach this frame to the body. It's like you have a gyroscope or an airplane, right? Yeah? Okay. And sometimes called the local frame, and this is the global frame. So the investor takes the global perspective, all right? And the CEO and the manager will take the local perspective, okay? Now, you can even have another frame. I mean, in aviation, of course, that's what you do. You have the Earth, and then you look at an airplane from the Earth, or you're the pilot and you sit in this airplane. That's the local guy. Then, when you're standing on Earth in your control tower, then you're more global, but really you're not global because the Earth is still turning. So if you're out in outer space and some drone hanging there, then you're going to see this guy in the control turning tower. You take an even more global perspective. Okay, that's what happens. All right, and that's the true inertial frame. So even this investor may not be fixed in inertial space. Remember, in economics, we also had an inertial space. That's when the demand is truly constant, okay? So some investors may also be, turning in their own way, all right? So there's always somebody out there that we imagine, that's what Newton's first law actually tells us, that there must be something out there who is really, going at constant speed, or that is, has true constant demand. All right? Okay? So then you would have a fund of funds, a guy who is investing and makes different, I don't know. Huh? Okay? So you can, the point of this whole thing is not to start discussing all the details, but give you this idea how you can use all these structures and then apply them to economic situations, okay? Huh? So Andre made this idea last time, and so I thought it through for 3 seconds. I realized, okay, it's immediately applicable, right? Okay. Okay, and then this was all in 2 dimensions, right? So in 2 dimensions, what does the the CEO do? Well, all he does is amortize or whatever, compound his earnings, you know. Huh? And then the investor, all he does is receive earnings or do capital injections, all right? Huh? So in two directions, as you know, there are two translations. Those are what the investor cares about, right? Okay? And there's one rotation. That's what the manager has to do, all right? The director of the company, okay? So the owners have two, earnings and capital, all right? And the director of the management has one, which is, you know, how fast and what way they're running their business, whether they're loaning or, you know, okay? Now, if you have three dimensions, everything becomes way more complicated, way more complicated. And the reason is, so let's first look at the reason from a physical perspective. So in three dimensions, what do you have? How many translations do you have? Well, three, right? X, Y, and Z. But how many rotations do you have? You would think in two dimensions I have one rotation, so in three dimensions I'll add one, so I'll have two rotations or something. But that's not true. You actually have three. So it jumps from one to three, okay? And the reason for this is that for a translation you need a line, a one-dimensional thing that you're sliding along, okay? For a rotation, and whether this is a shear or a hyperbolic rotation, that doesn't matter. You need two dimensions. You need a plane. A rotation happens in the plane, all right? So for translations, you count the numbers of orthogonal lines you can make, or you're non-dependent. And for rotation, you count the number of planes, all right? Now, how many planes are there in the plane? Well, there's one, right? And how many lines are in the plane? There's two, okay? In a line, actually, how many planes are in the line? Well, zero, so there's no rotations on the line, okay? Whoop-a-dee-doo. I'm okay with that. I didn't even see how you would do that, right? And how many translations? Well, one. On a point you have nothing, right? No translations, no rotations, okay? Right? Now we go to three dimensions. Obviously, there are three different directions, lines, but how many planes are there in three dimensions? Well, three. You can take the XY plane, you can take the YZ plane, or you can take the ZX plane, right? Okay? So you're going to have three rotations, and we know this. If you take your phone out or anything square, you can rotate like this, you can rotate like this, or you can rotate like this, okay? So there are three types of business that you can conduct when there are three things going on, okay? Right? So I looked around for a good example to do that, and what I wanted to do, like, it would have been easiest to build out the, you know, the shear model, and I started doing that, and it is easy, but the problem is it doesn't correspond to anything you know, okay? You guys know all of this. You get this in your first year, how to do rotations in three dimensions. So you just know all these little things that I'm saying. So that's why I'm going to take SO3, which is the group of different orientations in three dimensions. And that's what you call rigid body motion, okay? So it's more complicated, and yet for engineers it will be easier. If this was a crowd of economists, I hope it isn't, because they'll probably jeer me out of the room. But you know, that I certainly would not do that, okay? So that's why I'm doing this. So I look around for a, I'm going to look around for, what was I going to say? Okay, so I was looking around for a nice example of this, and I found it. It occurred to me that the Modigliani-Miller theorem, I don't know if you guys heard about this, on the capital structure is a nice example. Now, first of all, what is the capital structure of a company? Does anybody know? You don't have to know. But that's the way you structure your liabilities, okay? So you have your assets and you have your liabilities. Now, there are two different types of liabilities, depending on who you owe money, okay? So if you owe money, because you borrowed it, then you have these debt holders, and that's called debt. And if you have money because somebody gave you the money and you were allowed to use it, okay, that's what's called capital or equity, okay? So that's the capital structure of a company consists of two parts. This the equity part of the capital and the debt, okay? So you start a business, you need to round up some money. So suppose you yourself, you throw some money in the business and you own that capital. That's your capital, not the business, okay? So the business owes that to you, all right? Huh? If you buy shares in a company, then the business has to give you the, that's your shares, all right? So it can book that on his liabilities, and that's, just the share value. And normally they're booked at par, in Dutch agio, and it just says on this value we issued these shares and we sold it to people, okay? All right? You do debt, then you write a bond. It's called a corporate bond, huh? And then you say, all right, I'll borrow so much of your money and I'll pay you this much interest. If you have capital and shares, then you say, okay, you give me this capital injection, I'll pay you dividends, okay? It's called a dividend. So the moment you pay it to the, right? Now, you may elect not to pay it, but you have to retain it as earnings, but still it belongs to the shareholder. So let's just assume they pay it out in dividends, all right, just to make everything simple, all right? So you have this company, and there are now three things going on. It has the earnings, so all the earnings can be paid out how, right? There's only two ways. Either you pay interest or you pay dividends, right? So what normally happens is these guys go first, you pay off all the interest, and what's left, you pay as dividends, okay? So there's really three things going on. There's the company earnings, here's the axis of the earnings, okay? Then these can be paid off to the debt holders, right? In terms of, we have to pay interest on it, and or paid as dividends on the capital, right? Now, this is usually fixed by contract, how much, and this one you can decide yourself how much you do, right? So a lot of businesses will do that. So they have these S corps and everything, and the taxman forces to at the end of the year to pay out everything and dividends that is not in the company, right? It's called a flow through or something. All right? That's the way it works. Okay? So there's three things going on here. That's clear, right? Okay? So from the investor perspective, this center of mass here can move in three different directions. What are the earnings? How much did you retain? How much did you pay out in interest? And how much do you pay out in dividends? Okay? You see? Now, what kind of business now, the Modigliani-Miller theorem that was called after two researchers, Modigliani, who was at MIT, I believe, when I was there, and he got a Nobel Prize for this, and I think this guy Miller also got a Nobel Prize. And they everybody had a long discussion about what this capital structure is and why it was important and how you get the best structure, how you should divide up things in interest and dividends, and they showed that it's irrelevant. It's called the capital structure irrelevance principle. You can look it up if you feel like it, all right? And their reasoning was very simple, and somehow nobody had ever thought of it right. So suppose you have a business and it's all only pays dividends and no interest, and it's much cheaper than another business, then what could you do? You could just buy this and go borrow money, right, and then buy it, and you'll end up with the same thing, okay? You see? So they use these arbitrage arguments to show that the capital structure itself, which is then the thing you're arbitraging, should be conserved, all right? It'll be worth your while to go through that. I don't want to say too much. This is a nice example, right? So let's assume they all amortize, all right? I think they do close enough, all right? Okay. Then what are the three options? So let's first look at, so there are three planes. So you have the blue plane. I have here the blue plane. okay? And it's just the equatorial plane, all right? So when you rotate in the blue plane, what that means is that either you have all earnings or you move some of those earnings, you pay them out as dividends, okay? Now the blue plane is characterized as the way this works, and I'm going to use these quaternions to do this, okay? They have this I, but this I is not exactly the same as the I unit in a complex plane. What this I does, and I gave it this hat and this double arrow, what it does, it is the axis that's orthogonal to the plane, okay? So the I plane is given by this one axis, okay? And then you rotate like this. This is the blue plane, all right? Huh? That's different than this. It's not totally different, but different enough, than this, where you see it's just an actual dimension, all right? In the end, the same thing is happening, because what you can imagine, look here, there's no direction coming out. So you could imagine this is an I direction coming out, and this thing is somehow, the axis, and then you give this another name, okay? Huh? All right? But that's only when you look at the Lie group. Let's not get too, all right? In the end, it's all the same. Okay, but this is the picture that you need. This is the problem with these quaternions, is that the meaning of these imaginary symbols is just different, okay? And a lot of people don't get that, because this I squared is also going to be equal to -1, but it's saying that if you rotate this twice, there's another dimension here, which is the real axis that I haven't even plotted, that it's interacting with the real. Just don't worry about it for now, okay? All right, I'll show you that here, okay? Okay? So you first have to get that right. So we first have to list the planes, and each plane we characterize by imaginary number, unit, okay? All right? So the absolute value of this is 1, and if I square them, so I do 2, I'm going to get -1 in all 3 cases. All right? Now let's go a little bit further. Let's see what happens here. So if you move along this thing, then here is I kind of give this some meaning, okay? So you can draw this line here, and the slope of this line is the ratio of, depending how you measure the slope, of the dividends to the earnings, right? How much of the earnings you're paying out. So this is called the dividend payout ratio in this business economics, okay? So you can go along the slope, and this angle here you can measure, all right, and it's the arctangent of the dividend payout ratio, all right? If you go along the red plane, that's when you keep dividends constant, so the earnings are then paid as interest. They sometimes call this the interest payout ratio, but what's more interesting, especially for you, this is the debt service coverage ratio, or it is DSCR. That's the thing that you use, okay? Yes, because you have a debt service here. You have to service your debt, so you got to pay this interest, and people want to see how much you cover that with your earnings. So the sign gives you, okay, the sign gives you the debt that you have to, the amount of debt you got to service, and the cosine gives you how it's covered, all right? Now, for your research, that's really not so necessary, but, you can just throw it in there and say this is what's happening in your multiport model, but, it's interesting to see where this comes from, okay? You guys with me? This is interesting, And then remains the green plane here that I call the earnings plane. So you can decide to have, and this is the most interesting one for the capital theory. And this is what they normally will do, is the leverage. So if you turn here, then if you're paying all your earnings, so here it tells you how much you're paying in dividends to how much you're paying in earnings, in interest, right? Okay? A rotation along here. And what that will do is this measures your leverage when you go along here, okay? A levered company is the one that got a lot of debt, All right? So if you're paying everything in interest, you got a lot of debt. Okay? If you're paying zero interest, you have no debt. This all you have is capital, right? So the idea is that because the debt service is fixed, you know, and dividends are not fixed, is that a company with a high, high leverage are these companies, right? So they borrow a lot of money to do business, but if anything goes wrong, interest rates go up, or I don't know what, then they're in deep doo-doo. All right, huh? Okay.
You set the interest rate when you get the debt, right?
Yeah.
So how is it that it's fixed, or?
Yeah, then it's fixed, okay? But usually they got to refinance because these things go over a period. So that may happen, right? So if you want to buy this company, you want to value it, you're saying, well, they have this maturing debt that's some ridiculously low things. If I have to redo this, you know, I'll be bankrupt immediately, okay? But for instance, huh? So if they need more money, then how can they borrow more? Sometimes a company needs more money to pay its bills, huh? So they're just maxed out.
Yeah, so all these AI companies now are kind of over-leveraged, and they have problems if the interest starts rising because they cannot...
Yeah, so when interest rates rise, you see their shares just tanking because they got to pay more for their debt, and then the shareholders get less, but they're very, so they have a little bit of, a little bit of equity, and then the rest is all debt, okay, at serviced at some rate, okay. But as soon as this goes up, then they squeeze out a little bit of equity. So the shares have to dive in value, right? Huh? You see, that's what happens. So you can measure here with your quaternions. You can actually measure that. It's a nice picture, because there's a lot of concepts. And in business finance, you'll spend, this theorem takes a while and people start discussing it and da-da-da. And this one picture gives you a really nice, and it will also tell you what the dynamics is and how you can use quaternions to do it. So, that's right. No, that's right. So I put that down here, right? So here you also see that. So there's this I thing that determines your distribution, right? So how you distribute it between, you distribute, that's called a distribution, when you distribute it out the dividends, right? This is your distribution policy. So these are the policies. Oh, that'll be a little better.
The dividend is then the total dividends or the dividend per share? The total.
It doesn't matter. How does it matter? I mean, there's an amount of shares outstanding, you divide it by that, right? Or multiply it, right? It's just a homogeneous factor, Okay.
In this picture, this sphere,
Yeah.
is just for the example, like I can imagine different companies have different structures.
Yeah, so, but this is more topographically. So if it's a little bit of a cigar, what you'll do is you will scale it and it will become a sphere, and then you can use SO3. They don't call this rotations, they call this elliptical transformation. So this could be an ellipse. Where it goes wrong is when the ellipse breaks open, it becomes a cylinder. Then you cannot use quaternions anymore as it is, but then you can use another set of quaternions, So this thing becomes a cylinder and breaks open here, for instance, So it'll be land and you can only go like this, right? Then you'll have, you'll have these lines and you'll have one I, and then you'll have two lines, So you have one epsilon, and then you have I times epsilon. There's another epsilon, right? Okay. And when you're compounding, you'll get something like this, right? And then there'll be an I here, will give you a regular rotation. And you'll have some kind of J squared is 1 there. It's compounding, and then there's another one here, right? So if you do this J, and then you multiply it by I, then you're going to get some other K here, right? Okay. So You can use, that's when something starts topological changes, just global changes. You know, local change, a little bubble, that doesn't bother the group, right? Huh? But when it's really topologically different, when there's a hole or something, right? Huh? Then there's no way of scaling to get this back. Okay? All right? So then you'll just go to, see what I did is oh, wait a minute. Here, I'm going too far. What I ended up doing is just generalizing this thing. But you can generalize this thing. You can also put this one together with, look here, you actually generalize that one, right? And then you can do different combinations. So actually, this is a good example. This thing here, I mean, you can just put some other ones here, and then you can make a, all right? You can make a group out of that. Okay, so the different combinations of this one amortizing, this one just yielding, that one compounding, and you get all different Lie groups. And all of them can be handled with some kind of quaternion. So in 3 dimensions, all the quaternions will work. All right? I checked it. Yeah, because a lot of them are just not so well known. I mean, split quaternions are, and the ones with the dual ones, they use them in robotics for translations, but not for this kind of problem. So I had to go check them that it all works, but it did. It's just, you can easily check it. You just, But here's the thing I wanted to emphasize. So now we know what I, J, and K are, but, and this should have been hats here, okay? All right? But now you can also see that one way to, you know, change your debt, what is it? What am I going to do? Say I want to change my debt service coverage ratio. What I can do is first, you know, change my dividend payout ratio, and then change my cost of, this one here, right? The way I leverage it. Okay? Well, you know that. You can get this rotation from first doing this, and then, I don't know, You know how you can get another, if you take something like this, and you rotate it first this, and like that, it's the same thing as rotating it like this, right? So you do 2 rotations after each other, you get a third one, right?
Tracking the point on the surface, right? Like if you're just tracking the where you are on the...
Yeah, then it will make a thing. But you have assets and liabilities. So you're in the plane, you see? If you're just checking one point, you don't have double entry, so you don't have a rigid body. You just have this one point. Now you can go whatever you feel like, right? But if you're rotating an entire rigid body, you can't do that, right? So if I take this, as it's not very rigid, but you know, whatever, and I go like this, and then I go like that, I can also go like that, right? Okay? It's just, they're not commutative. That's what this says. If you travel in space, you can go like this, you go like that, and then you don't do anything else, that you do this or that, you know, it's not commutative, okay? So you can get, if you have 2 rotations, you always can build the third one, okay? It's like parking your car. If you can drive and steer, then you can go sideways. Although you can't explicitly go sideways by compounding together small drives and small steers, okay? Steers, you see? That's what makes this hard. See, in SO2 is not the case. You go chak chak and you go cha cha cha, no difference. For the translation group, it doesn't matter, right? Here it does. So there are multiple ways of running this business. If you can't really do this, you know, we can only legally do the others, you can effectively do that. That's what this is saying, okay? Now, if you know this, so you can work your way at home through that, why this makes sense, okay? But it does. I did it. And it just makes sense, okay? See, whatever, you can also say these are 3 types of goods, and I'm into this trade, and then into that trade. Well, I could have done directly that, right? But suppose I don't have access to that. I can first sell my chicken for eggs, and then turn my eggs into money, and then I've effectively turned my chicken into money, right? That's what's going on here. All right? So that's something, of course, that Modigliani and Miller, not that they were looking for it, but is hard to understand. But if you think through it, you say, of course it's true, and probably every CEO will know this, right? Huh? But it's nice that this. So if you check this, and you also check that I squared equal j squared equal k squared equal -1, then you know you have quaternions, okay? Right? Okay. Now here's the magic. So this is what is called the Lie orbit. So these are, just so like the quadratic example, these are infinitesimally small rotations, okay? Huh? So these are infinitesimally small dividend changes in these things, okay? So how do I integrate this out? Well, I'm making, all the time I'm adjusting my policy, and I want to see what happens when I do this, huh? At a constant rate, all these things, right? Okay? How do you do that? Well, let's go back to the simple two-dimensional example right here. Well, I'll go right here. Huh? This one here. Now, if I know that here is the I, just take the I-axis, forget about that it's here, just put it over there, all right? A tangent to the surface of the sphere. I know you think of it being here, but forget about that for the moment, right? This is just a plane in which the rotation is taking place, and I just took the I-axis and I plopped it here, okay? So I'm making an infinitesimally small thing, and then I want to go further, and I go out, and then if I do that clever, then I go here, and I go, and then it goes up, and blah, 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 and then, say, I don't know, something like that. And I work through this whole thing, exponential map, and I'll end up here, okay? That's what's going to happen if you do that, all right? So it's like taking a little rope, and making it very flexible so that you get all these little vectors I, and just wrapping it around, all right? And then measuring how much you wrapped. That's what the exponential map does for you, all right? Huh? That's the trick. Then you see also why you start out with an imaginary number, and presto, you got a complex number. Because while you're trying to figure out how far you go, you have to keep track of this number, but also of this number, because the total makes, this position, okay? So although your tangent plane, this is the Lie algebra, right? It's called the Lie algebra. It's called the Lie algebra because you can multiply them with each other, right? And you can also add them, okay? Yeah? Is here one-dimensional, the whole group, all the orientations can all be plotted, it should be plotted in 2 dimensions with a real axis, And the real axis tells you really how long you've worked at this, okay? So how far time has passed, okay? That's what it tells you, huh? And then imagine the sign will tell you how much you've actually amortized, okay? Now, so that's something to keep in mind, because nobody ever understands why quaternions are 4-dimensional, right? Because why do you need 4 dimensions to rotate and the rotation is only 3 dimensions, okay? And the answer is it's the same as why a rotation in 2 dimensions can be done with 1 dimension, but if you want to plot it out for a bigger thing, you need 2 dimensions, okay? So what you do is you take this 3-dimensional little cube, and you think of yourself as sitting in a 4-dimensional space, and you take a sort of 3-dimensional sphere that's embedded in 4-dimensional space, and then you just take a direction in which you have your cost of equity, your debt service debt, and then you integrate it out. You see where you end up, all right? If you do that, it shouldn't come as a surprise to you that I'm going to get this, okay? The exponential map of this combination of imaginary numbers. So this is the rate at which I'm distributing, this is the rate at which I'm leveraging, and this is the rate at which I'm taking risk, okay? Huh? Okay? Right? Okay? Now this thing is going to be, this is called a vector, and if you sort this out, you're going to get some quaternion that's got a real part, huh? Some real part, omega, huh? T or something, I don't know, A, you know, plus all these imaginary parts, okay? So you'll get a four-dimensional thing, all right? Now, the absolute value of this thing will be 1, just for the same reason that any exponential map over a complex thing always gives you absolute value 1. Hamilton called these things verses, okay? So quaternions in four-dimensional space, because its absolute value is 1, you get a three-dimensional sphere in four-dimensional space, okay? Because it's 1 constraint on the 4 dimensions, right? This number gives you the orientation, right? It tells you how much you have done all of these things, okay? And that's what the quaternion does, all right? So don't try to understand how this works in four-dimensional space. Just the trick here is when you know something works in the small, huh? In the Lie algebra, it's just a question of integrating out to figure out where you end up, right? This is the one you got to understand, all right? Huh? When you understand this, all right, okay. Just use the exponential map, all right? All the information is in here, okay? Again, okay, you might as well call a Lie algebra. Well, first of all, these are vectors, so they're tangent vectors on this big thing, huh? And it's called an algebra because not only are they additive, like all vectors should be, huh? But you can also multiply them with one another, right? So an algebra is when you can add and multiply. That's why it's called a Lie algebra, okay? Okay, that's all. But these are just fancy words. I mean, the point is you got to understand, okay? This is how they work. All right? Now, to be really honest, okay, so here is this Hopf vibration. So this is what you get when you do this business. So you're going around in this three-dimensional sphere. Now, how do I plot a three-dimensional sphere? You can't really, but Mr. Hopf, he figured out that what you can do is take a two-dimensional sphere, here it is, right? Huh? And see that as the direction, your instantaneous axis of rotation, and then you tell me how much you've rotated around that axis, okay? So that's 1, 2 parameters for this and 3 for that, okay? So you have a two-sphere, and on each two-sphere, you have attached to that point is another circle, huh? Okay, right, huh? Right, huh? So the circle is also a group. So what we say is we can factor out the bigger group, SO3, by having one, circle, and then a bunch of cosets, a bunch of this circles, all these spheres that give the direction of the rotation. So that's how you would do it at Euler angles, right? So something like that. You would first give the direction, and then you say how much you rotate. Huh? I don't know. There's all kinds of tricks, okay? And basically, that's what these quaternions do. So they'll, huh? Okay? All right? Huh? And that's called the Hopf vibration. So you'll see that as you change the orientation of the sphere, this circle that belongs to it, has to be a different one, and they all start interlocking like this, Okay, that's what happens. They're not just like a cross product that you just plus it on, they start interlocking, so you get this interlocking set of circles. That's called the Hopf vibration, all right? So it's called a vibration because for every rotation direction, you have a fiber of circles, okay? That gives you the whole group. But look, you can talk forever about this, but and people study this. This is from a guy called Niels Johnson, which I really like. But the reality is, if you understand this thing, you're basically there. All right? Now you just have to trust. Well, the good old exponential map will do the job for you. All right? Huh? Okay. So this is really my my thing here is it gets harder to understand these things because everything gets, you know, and here everything is nice and linear, you know, it's just vectors. Here, these are not, orientations are not vectors. They are really complicated objects, you know. It's hard to understand, so we try to avoid that, and we do it this way. Huh? Okay? Now, I'll make one more kind of disclaimer here, is that I said SO3 for the special orthogonal group in 3 dimensions. Really, quaternions, they are another group, it is SU2. It's a complex group. Or the quaternions is the same as this. And it's a double cover of this one. It's a little bit complicated. And because the problem with this quaternion, like suppose you have a rotation, you have this direction, and then I tell you how much I rotate. I could have chosen the opposite direction and rotate the negative thing. It's the same rotation, right? So that's what they mean by a double cover. So what you do on your asset side, you can do your liability side, and vice versa. It makes no difference, you know? Huh? That's really what it's saying. So that's how you can keep it in balance. So because it's a double cover, you can keep track of both assets and liabilities in this capital structure, all right? So I don't know, huh? In practice, you don't use it that often. What really happens is, well, I don't even think that's true. I think what it does, okay, here's what that double cover does. It gives you the relationship between you and this investor in some weird way. It's called entanglement, okay? So there is this thing called the Balinese plate trick or Dirac's belt trick or something. Have you guys heard of that? Huh? But there's this trick, I can never do it, huh? Because I'm way too stiff and stupid for that. But you keep your plate, you can kind of rotate a 360 by, and your whole arm will be messed up, right? The plate will be at the right position, and your arm will be messed up, right? But then if you keep rotating another 360, everything will sort itself out again, right? You know this thing, huh?
A colleague of mine could do it.
A colleague of yours could do it, huh?
Yeah.
So what does that mean? So you got the plate at the right orientation, right? So the plate is in SO3. So that's the rigid body, okay? So the business is at the right thing. So management will be okay. But this plate is attached to you via your arm, and otherwise they do it with a belt or something, where they have the belt buckle and then they, huh? So what is that attachment? Maybe that's the investor. And so after a 360, if the investor still, from his perspective, there's still something weird if he is attached to this thing, okay? That's the only way to view it. I haven't thought it through yet entirely, okay? So it says nothing about the rigid body, but if you attach it to its environment, how that attachment goes. That's what the double cover measures. So normally we leave it out. It's not interesting. But I was thinking I'll give this as a nice side note. Huh?
They also use it a lot in robotics and aerospace.
Yeah?
Yeah,
What do they use it for? Huh?
you use Euler angles
Yeah.
to get singularities.
Yeah.
Gimbal lock, exactly.
Yeah, gimbal lock. Yeah, and with this you don't need it because you have your double cover, right? Huh?
It's like
Yeah.
in standard robotic messages, they give the quaternion representation.
Yeah. But is it because of the entanglement? I'm not sure it's because of the entanglement.
Because of the gimbal lock, you get.
But is that due to entanglement? That's the question. Because quaternions will do this right. But if you use...
I think if you have the pitch and the yaw, at some point if you pitch high enough, then the pitch and yaw become the same.
Yeah, no, I know that. That's because of the choice of angles, you see. But this has nothing to do with that, you know. This is only if you attach your rigid body with a belt, you know. Now, they don't do that in aerospace, attach their airplane with a belt to the ground, right? Well, some guys. Huh? Not yet.
Maybe in the future.
Huh?
Maybe in the future.
Yeah, so if you have something flying and you got some tether cable, then you need it, right? Huh? But the gimbal lock you don't get here at all because it's a coordinate-free representation, right? I mean, you're just out of your Lie algebra where everything is fine. You know, you just keep integrating out. Huh? So
I think they fix it, the gimbal lock issue with this.
Yeah.
I know that, but it has nothing to do with the double cover. That's what I keep saying. See, remember, this is basically coordinate free, right? I don't care. This is just some vector. You know, I happen to choose I, J, K, but it doesn't matter, right? So this is totally good. And the exponential map is coordinate free. So the Gibble lock has to do with the fact that your coordinates are such that two of them tend to line up, right? Huh? Yeah, but here that can never happen. You know, you see, huh? So that's separate. That's a separate issue.
It's the group action, no? It's called, isn't that what it's called? Like the Euler angle matrix, the matrix that you have to rotate with the 300.
Yeah, that's the
That's a group action, and also like a quaternion multiplication is also
group. Yeah, this is what happens. Right.
Action.
Yeah.
How, I don't know why.
No, it's the same group action, but a different representation. Okay, that's what you got to see. Okay, so some representations they're better than others. So if you take some group and you want to have a matrix group, you're going to flatten it out in this matrix space, and that may not work so well because you may not be able to cover the whole group, right? Huh? You see. So the group has no problems. The group is a differential manifold.
It's in the kernel of the operation, like you can't.
Yeah, but only when represented in these coordinates. So here, if you do a rotation with a versor, you'll take some kind of object, you know, with an orientation, say Q, yeah, I don't know, orientation O, so, and then you do Z, and then Z minus 1 here, so you do the sandwiching, okay? Just like you would do a similarity transform, you know? So you keep changing the coordinate system, okay? I will come to this later when I do pricing, all right? But the problems are all in representation. So just like manifolds and coordinates charts, manifold is just there. It always works because it's the theoretical thing and it's working. I mean, the economy is working, your physical thing is working, all right? Then if you represent the action in terms of some coordinates, those coordinates may have singularities, you know? If you try to map the Earth using a Mercator prediction, you also have singularities at the pole, for instance, you know? So it just screws up. But what does that say about the Earth? Well, nothing, right? You know, the Earth doesn't have any problems. Your map has got a problem, okay? So these matrices, they flatten the whole thing out, and then you'll run into trouble. But if you use quaternions, you're not flattening anything out, you know? You're just using something that is inherently, you know, okay. It will always work, okay? Huh? That's the point. And they're super efficient. But I also like them for understanding what's going on. Because these rotation, you know, they're huge matrices. Well, there's a 3 by 3, and then for an angular velocity, you got all these zeros here, and then a couple, and then a minus sign here. They already see the problem. Then we'll have to remember all these zeros, and then this is minus that. There's all kinds of symmetry in this thing, right? Huh? Whereas here, you just say, okay, I squared is minus 1, and a bunch of these things that show how they commute with each other, and then there you are, right? Now, of course, I can take this and represent it with matrix. So I can take a matrix and then square it, and then find out that I get the minus identity matrix, you know, minus 1 minus the identity matrix, right? Huh? Something like that. Of course, I can do all that, but it's just so cumbersome, right? Huh? Just to understand what's going on. Huh? In 2 dimensions, you have the problem already. Like 2 dimensions, use of I, you know, or you have to write, what is it, 0, minus 1, 1, 0, or something, right? Huh? Now, this is a matrix, and if you square this, you'll get minus the identity matrix. Huh? This is equal to 1, 1, 0, 0, minus sign. Is that obvious? No. Huh? Well, it seems to work because this times that, this times minus 1, you know, huh? That's 2 dimensions. You know? So matrices, they really are not so great for reasoning, you know? One of the problems of control in a lot of engineering is that they got stuck on this column vectors and row vectors and matrices, and then you have guys with papers with tons of matrices, gazillion matrices, all multiplied. You know, it's very complicated, huh? And then you lose the intuition, you lose the basic ideas, huh? Only to find out that these things suffer from gimbal-like, and then we might as well go back to these quaternions that were developed there somewhere in the 19th century, and they're way better, you know? And in the end, we just have to understand it, and then if we do, then we immediately have a solution. So, yeah, modern engineering, I think, is trying to get away from this because just these approaches, they just have a lot of value, you know, and they've been neglected. It's a bit of a sad story because Hamilton came out with this. When did Hamilton come out with this? Do you know, Wesley? Huh?
1860.
Yeah, somewhere middle in the 19th century. So that's like more than 160, 170 years ago now, right? Huh? That's even long ago for my standards, all right? Huh? Okay. And then there was this other guy who was also excellent researcher, Gibbs, and I think also Kelvin, who just didn't get it, right? He said, this is junk, this doesn't work, right? Huh? And then Gibbs went ahead and he did his vector calculus, and that's what, and he defined the cross product and dot product. They wrote a book on how to do vector calculus, and then everybody said, oh, okay, we can understand that. You just plug in these numbers, you know? And then everybody started doing that, and then it's only until recently that they had to do all this 3D stuff on computers, you know, with drones and also in animation, Pixar, you know, those places, they just couldn't do it otherwise. They had to use quaternions. All these animated movies are chock full of quaternions. So if you look at Emil's thesis, he looks at the spring mass damper system from a quaternionic point of view. He uses this SO21 group or something. Huh? It's super efficient. You know, you immediately see what's going on. Huh? Instead of all these complicated things, you know, huh? Like underdamped, overdamped, critically damped. So all kinds of singularities there. So if you increase the damping, it would go from underdamped to critically damped. You need a whole different formula for the, huh? You know, instead of sine and cosine, you have to do, one, you know, you have a damping factor, then 1 plus VT or something, some linear term, right? Huh? And then when it's overdamped, you have these two poles on the real axis, you know, well, where did that come from, right? Huh? So these poles in the pole plane, they're going like this, and they crash, and go, you know, we sit there with all this, but nobody understands. If you just looked at the group, you'll see this is just a poor representation of what's going on. But I'll stop my preaching now and get on with it. You see, huh? So I am a big fan of going back to, you know, just the intuition. And the problem is, if you open up a book on Lie group theory or symmetry with Lie groups, there won't be a single picture. And it will all be theorem proof. It's just inaccessible, okay? Huh? And these mathematicians, they're worried about other things. They're worried about whether it's consistent. And I mean, they're engineers, you know, I don't care that much. But the idea behind it, that's the excellent thing, okay? Huh? But that then gets lost in the shuffle because of the diverging, you know, engineering from the math. And then once in a while, somebody says, I need it, and then, huh? Huh? So that's one of the things that's kind of wrong, in my humble opinion, with modern science, is everybody got so specialized and, you know, published, I don't know how many papers. I mean, if Newton had it, but Newton, how long did it take him to write his Principia? 20 years or something, right? Huh? He would never have gotten tenure at any research university with one publication after 10 years of it. Huh? So he would have immediately been flushed out. Okay, so now we did a really non-trivial examples and example, and I could actually go on. It's very interesting, this stuff. I go on, huh? But we wanna make some progress. So all we did here is talking about how goods move, right? This is all money movements, right? Nothing to do with value of why we should have such a movement. So we want to start looking at the causes of this, all right? This is economic engineering instead of economics, all right? Economists, they are not so interested in the causes. They do a lot of, especially econometricians, they might do some good data fitting and this, all right? We're going to look at the causes of why the trade, what's the drivers behind these trades? What are the incentives, Okay? And that's what brings us to our next topic. You have trade, and then you have to have a theory of value, okay? That people assign some kind of value to each good that's being traded. And there has to be a theory that tells you what the relative values are, and then the values are personal to you and me, and they can be different. And based on these different valuations, we have a driver for trade, okay? Rather than there's a description, the comparison of these values will tell us what we want, what we will do, okay? First, as a single individual, and secondly, when we work together in groups, okay? All right? So that's where we're going to go now. So all this next will be about value. This is also where you think, how hard can it be? Well, if you look it up, the theories of value on Wikipedia or something, you'll see there's a whole bunch of them. And there's no agreement in economics on how to do this. All right? So I'm going to give you a theory of value here that's actually like the theory of the trade, just purely coordinate invariant, okay? And the way I'm going to do it is I'm going to take the picture we had before. So that was that you had a timeline, and the timeline gave us some kind of course of action, okay, by mapping in there, all right? And then you knew, you could determine, they had the description of how the trade went. So this is how the stock quantities of everybody goes. And then in the tangent plane that I haven't plotted here, but I put the line there, but the plane itself is blue and it's not there. All right, I plotted another plane, which I'll explain in a second, okay? All right, that's what we had, all right? So now look at now the simple idea, all right? So if you can have a real line, we all understand that time is on a real line, okay? We all understand how you can take something arbitrary, fuzzy, and map from your real line into that thing, okay? And if that thing is smooth enough, we'll see we get some kind of path in some ridiculous space. What's the other thing that might be easy to understand? Well, that's the conjugate to this, in a certain sense. That is, if we take any point on this space and just map it into the real line again, right? Okay? In doing so, we have two mappings. We go from the real line, the time, how time is progressing, into this amorphous thing, all right? But at the same time, we're coming out and we're measuring something. What's happening, all right? You see that? So if I leave this all out, I just have a function that maps every time in time into this thing, okay? All right? Now what is this thing going? That's the mathematical setup. So you see, this is the solution to everything, to manifold theory, okay? Now, when people talk about, economists talk about value, you can look it up, they'll say, well, it is a measure of the economic benefit or economic cost associated with something, okay? So somehow a value theory has to be built on that. So what did I choose for this function? Well, what I chose was something that measures the total net economic cost. I should have chosen the net economic benefit, but unfortunately, if I put that doesn't really jive with the mechanical engineering, where we have something that's very so analog to this. It's called the mechanical action, okay? So for the benefit of that, I put a minus sign in front of it, so we don't maximize it, but we minimize it. So all our formulas will change up to a minus sign, but they will be consistent with the classical approach in mechanics, okay? So this thing is called the action. I don't know, the US action is really overused, but that's just what they call it, the mechanical action or something like that, okay? In this context, it's sometimes called Hamilton's principal function was, you can remember all of that. But the most important thing is to realize is that what we're going to do is we're going to associate with every point here something called the amount of cost that we accumulate, net cost. So the benefits minus the cost, or cost minus the benefit. Right? This could be a negative number. As we progressed over this path, all right? Okay? So instead of doing this like a flat, like we think of time, I would think of this as a level, right? So it's one of these level gauges, you know, that you can put out in your river and look, you know, one of these, I don't know how to call them. There's a staff gauges, I think they're called in English. You know what they are, right? So you put this thing with some lines, and then you can see how high the river has come, right? So I like that because, you know, benefits or the cost or the value, you know, it has the idea of a level rather than a motion, right? And we're changing the level, right? So here we're at 0. You started at wherever you are, and then it just increased as we go through this path. So I put the path here. This is the initial point. This is the final point. And then we're right here. Okay? All right? Clear? Now what happens? Here, we let time move forward in infinitesimal amount, right? That was this vector here. Here, we want to increase the level at an infinitesimal amount. Now, rather than ddt, you've got to look at some ds. So it's some small change in this, the net cost, okay? Net economic cost. So what I will do is rather than plot it like an arrow, I'm going to plot it like 2 level lines, right? So here's where we started, and here's where we are, and then, okay, then this is that vector, okay? It's really not a vector, it's what's called a covector, right? All right? So the vector here, that's how time progresses. That pushed forward here, okay? And that ultimately pushed forward here. So here I see it, it's just running up like that, okay? And this thing is here, and you can define what this is, and then it pulls back. We call this the pullback, because it pulls back on the surface, all right? You see that? So this thing corresponds to that, and there it's called, yeah, it has a name. We'll talk about this later. In mechanics, this has a name. It's called, I'll call it the price gradient, okay? So, okay? We'll find out why, yeah.
I don't really understand why. I understand why the time will be taken infinitesimally small.
Yeah.
On the right, like the price can also change a lot, right?
Yeah.
Why is the change there in like ds?
No, the time can also change a lot.
Yeah.
That's not a problem. But how do I see that? I see this change as made up of very small motions, very small increments. And I integrate that out, right? Okay? You see?
Yeah, so this ds on the right is not per se linked to the dt. But
No,
yeah, okay.
totally different. That's what I keep saying. You can forget about all of this, right? And then just take that. In fact, I did that over here. Here. Okay? It's just, okay? But I just wanted to show you the symmetry, right? That on the one hand, we are doing this execution, then we see what happens in some new space, and this is another step we do. It's not really bookkeeping, it's valuation. We assign a value to these motions, okay? And we can also assign infinite values to infinitesimal motions, infinitesimal amount of demand. You know, what if I'm buying more at this rate? How fast will I accumulate cost, okay? All right? So the way to view this, I mean, this all makes sense, but it makes even more sense if you think about it. Just say you're climbing on a mountain. So in Holland, that's problematic because we have no mountains, but you're going up the dike, okay? Huh? And I mean the dikes we have here, okay? Huh? And so what happens? So suppose you're going, you went on your vacation to the Alps, and you want to do a hike, all right? Huh? So what will you do? Well, you'll get one of these hiking maps, and they're topographical maps, right? So they'll look like this, and then there'll be these, huh? These are the level lines. So this will be 1, this will be 5, you know, I don't know, 2, and this will be height 3, you know? So when they're close together, the mountain is quite steep, right? Huh? Okay. All right. So that's just a description of the mountain. That's how you have to view this, okay? So that's why I plotted like this. This is a level. This is how high the mountain is. Then this is the Earth, and you know, this is how the Earth goes. And at every point, I give you just how steep the mountain is here. Huh? Okay? That's what I'm doing here. All right? Huh? Now, how does that relate to how I'm walking on the mountain? No, it doesn't. It just is purely a question of saying how much height I'm accumulating. And instead of height, you should now think value, economic value. Huh? Okay? Okay? Total amount of benefits that you are accruing, that you could be accruing if you were doing it. But you're not doing anything yet. You just described what happened. Okay? Now that description can be made complete if you make these topographical maps. But what do you do when you do that? Well, you say, suppose you're here, then I can straighten out this level line a little bit, right? Huh? Then I go to the next one over, okay, it's here, and then I have to flag the uphill direction, that's all, right? Huh? How is that different from this, right? And then here, I'll do, I do it, flag this one, and then it's, this one, and then I flag the uphill direction, right? And I call that alpha, right? Okay, so what is a vector? It's just a straightened out tangent, you know, of a line. And what is a covector? Well, it's just a straightened out level lines, okay? Where you see. The only trick you have to see is that the closer the covector lines are together, the higher he is, right? So that's why I called contravariant and covariant, you see? Because you know that when the level lines get really close, that's bad news, okay? Right? So here, if the level lines get very close, you're accumulating a lot of cost, all right, for the same distance, all right? Now, I kind of went a little bit too fast for that last thing, but suppose now you're going to climb this mountain, so you got this topographical map, right? Right, here it is, Now, if you're here, what can you do? Well, you can go straight up the mountain, okay? And then if you do that, you know, you're accumulating 1 meter or 1 kilometer, I don't even know, right? But you can also decide to go this way, right? Or you can decide to walk very slowly, right? See? So this thing tells you how fast, in what direction you're walking, right? How fast, that is how this is, and the direction, that's the, and this thing, this green thing, tells you how much cost you're accumulating given the direction and given how fast you're going. But you don't have to do that. You can go this way. You can go through this path, you see? So you see how this picture pulls apart the trade itself from the valuation aspects. In the same way that a picture of a topological card, topographical I think it is, topographical card, gives you only the valuation, and a plot of your route, right, will tell you how you're doing that, and you put those on top of each other to figure out what you're going to do for your hike, okay? All right? So you can view this as a hike in economic space. So every economic action, when you evaluate it, you can think of it as a hiker going on, but you are in this hilly landscape. Things have cost. If they didn't have cost, you could go skating along, right? You can buy anything you feel like, right? And dump anything you feel like, all right? But you can't. So there is some cost structure. We haven't said which one yet. All of that will come later, all right? Okay? I just want first to define what I mean by value and cost. Okay? All right? Now, why did I call this the price gradient? And we'll find out exactly why later, but it makes sense, right? So this is your quantity demanded. So this tells what quantity you're demanding. And this is how much cost you're accumulating. Now, if you know how many barrels of oil you're buying, right, then what do you have to know in order to calculate your cost is multiplied by the price, right? And that's what this thing does, okay? If you know how fast you're walking or hiking, all you have to do is multiply it by the steepness of the slope to know how much you're going up per unit of time. So you see, that's how this, together, this determines at what rate you're accumulating costs. All right? Now, in the end, we're going to use this and say, we're going to try all kinds of different paths and see the one where we accumulate least cost. Okay? All right? So it's a purely geometric description of the valuation structure, the cost and benefits associated with little infinitesimal actions, right? Okay? And the separate structure that gives us the freedom to choose between different paths, right? Different courses of action. All right? And this together, that will put us in a position to calculate the equations of motion. That is, what is the agent actually going to do if it maximizes its benefits, net benefits, or minimizes its net cost over a period of time, right? And in the end, we're going to find out that that's exactly what we're going to, in the Newtonian case for commodities, you're going to get exactly what you guys are calculating in the multiports and all of this, and it will all work out, right? But this will tell you, now what the foundations of this are, and what you got to do in more complex cases, like with the capital structure, okay? Because we all know these can be nasty, nasty, nasty spaces, yeah? And that's not just some, theoretical statement. It's just a simple rigid body or several economic examples that are very common, and every textbook have already quite complicated structure, okay? All right? Okay. Now, so what I've done now is instead of economic state space, we had this before, and that was just, let's go back to it. And I conjured that up so that you could keep track of what the stocks are and what the quantities demanded are, right? All the flows are. But now, forget about the flows for a second. We want to keep track, of course, what the stocks are, right? But we want to keep track what is the marginal cost here, okay? Which we'll call equal to the price, all right? Okay? So we need instead of that tangent space, we need another space, that acts well with our tangent space of flows, by using so I can calculate time rates of things, And that space is called the cotangent space, okay? Because it has a covector instead of a vector, right? So the one has all the tangent vectors, okay? This has all the covectors. And they're called covectors because they covariant with so that the inner product will remain constant, as we'll see. All right? Okay? And this is the cotangent space, and it's usually indicated by putting a little star there. Okay? But this is the cotangent space at any stock level Q, right? So you need one. That topographical map has to be all over your manifold. You understand that? So you need a cotangent space here. I should do them in green. Here, you need one here, you need one everywhere. So you put them all together, you get the cotangent bundle, right? That's something called T star of Q. Okay? All right? And this one, our example of this that's familiar to everybody, and I'll go through it, but let me just say it now, is the phase space, right? So the analog to this price is actually momentum, okay? And normally, if you draw phase space, you'll have Q, but instead of state space, where you drew Q dot here, you'll draw momentum, right? And that's what you call phase space. Now, you can say, well, momentum is related to this and this way. It's okay. It's not always, huh? You know. What you got to see now is that you can define momentum separate from this law that it says P is M times V. It's just there. Light also has momentum, okay? And it's not M times V because M doesn't even exist. It doesn't have mass, okay? So the realization is this is really a different space, okay? Okay? All right? We call it the phase space. So I call the tangent bundle the economic state space, and I call this the economic phase space, you know? Huh? That's why. Huh? I don't really like this word. Gibbs chose it because where's the phase? I mean, he thought of an angle or something, harmonic oscillator. I don't even know. Huh? But the terminology is well established. All right? Huh? I don't really see the phase very well. Huh? Huh? Especially not in the definition. We don't even have a notion of angle, but all right. Huh? So here's the picture. All right. Any questions? You're going to get used to it after a while. You're just so used to it, and it's okay. The beginning, it requires a little, all right? Huh? But you're going the right way. First, you already realize yourself you're commingling everything, right? Huh? Yeah. All right? Okay. So now, let me move on. All right, so now you said, hey, wait a minute. What happened to the coordinates we had, you know, or a coordinate chart and something? Well, you can put those on too. So you can, you know, they're chosen so you can go either way. So you can put some coordinate chart here and do that. So that's what I'm going to do in the next slide. Let's forget about this for a moment. Otherwise, the slides get a little busy, and I will put a coordinate chart on it. And then it becomes a little bit more intuitive. All right? Huh? So I did that here. So here is your price space and a stock space. So think about this. Let's first think about this thing as being, now let's first explain it. No, let's first do the intuition. Why do I look at the combination of a point in stock space here and a price at the same time? Well, the better question is, why not? Because if I go to the grocery store, what do they know? They know how much they have, and at each different article, they put on a different price. You can't switch the prices for the article, and when the stock goes down, you know how that is with airline companies. If the chairs go, the price will go up or down, okay? So it's going to depend, you always do this. So you got to find the right, good, and then attach a price to it, but only at that stock level. There's no reason. If you go to the grocery store, they tend to hold it a little bit constant, Actually, it's not really a price because it's how much money they're willing to exchange for it. But, even that is a little bit different. But if you think about your own price that you're doing, it's for every stock level, for every good. So you got to go in this cotangent bundle. You need to keep track of all the Q's and a P at every Q, right? This is just how it is. If I see the price tags, that's what they do, okay? So it seems complicated, but really it isn't, okay? It's just saying, all right, huh? So a price without the good associated with it, and the stock is nonsense, okay? Yeah, what do you do with that? It's just the price, That's why you need this whole space. This is the complicating factor, All right, huh? This thing here is also called the tautological one form. And it's called tautological, but it seems, because it looks complicated, but then when you think about it as a mathematician, it seems trivial. And but nobody can always get people confused. But if you just think of it as like, okay, of course it's tautological. You just all you're doing is attaching a price to, but you're looking at the bigger space, okay? But you don't want to see a price separate from the stock that it pertains to. All right? Okay. So that's the intuition about this big space. Is just going to your grocery store and you see it right there. All right? Okay. All right. 2 more items left at this price. The other ones are going to be higher price. Okay. So. Now, of course, this has to be reported in some way. So what does the grocery store do? And again, those prices are money prices. I'm now thinking about you. What will you do? Well, what you do is you'll first make a catalog. So what does the catalog do? It really just says these are the type of goods that I'm considering, all right? So that's Q1 through Qn, right? So you go to these internet sites, and it'll show you all the products they have, all right? You can buy a SD card, this and that, right? Then they'll show you how much they have in stock, right? So 5 left, okay? So how would you call that? That's just an inventory report, right? So these Qs here, they get mapped out to this inventory report, all right? So this position here says so many SD cards and so many of these tripods. We just bought these things a while ago. That's all it says, all right? Okay? Then the price here, that's just, what do you do there? And then you have to say, okay, what price is it? And they give you the price. In the old days, you would get a price list, you know, now, the different prices. Now you click and they show you the price. Sometimes you can ask for it. So it's a separate thing, the price. Okay, first you look at its inventory, then you go look at the price, all right? So that's called a price list, okay? So the way to look at this big space is just, as a one big inventory report here, okay? Plus, at every point, the price list, okay? All right? So that's the way you put coordinates on it. So compare that to the balance sheet and the income statement for the flow statement for the actions, okay? Now, of course, you know enough that if this is SO3, there's also prices going to be associated with those positions. This is not going to cut it. I mean, you're going to have some patches, and you're gonna do some complicated stuff. That's okay. All right. Okay. So this is also called an inventory valuation report. I actually looked it up. So it's got an inventory. But they also value it because you know what the price is, right? So a company does that. They value their own inventory, and they'll write this report, okay? Really, all we're doing is, having a look at these cotangent bundle, all right? And there's different ways of doing it, Okay? All right. So the map to from economic space to these inventory valuation, I call it cataloging. I kind of looked it up, and that's what they call it. Doesn't really matter exactly how you call it, as long as you realize the simpleness of what is all happening here. All right? Okay? All right. Now let's move on. The good thing about these inventory reports is that it becomes much easier now and I skipped over something here. So let me go back here, all right? And then I'll show you. But I like the way I did it because this gives you more feeling. So forget about now your inventory report, right? And you just have this picture. And now I want to tell you how this thing works. Okay, so that was the long story I gave you. So there's something you would call the flow of value or a value flow. So at every time, this is your quantity demanded, and this is the price, okay? Now, how do you calculate this quantity demanded? Well, it's actually geometrically quite easy to do that without any coordinates. You just see how many times these level lines fit in here. So this one is approximately 2, right? Huh? So if you measure this in dollars and this in days, right? Huh? Then you're spending here $2 per day. Okay? All right, think of these as level lines on your topographical map. You're going at a rate 2, and you're crossing 2 of these level lines, so you're making 2 meters a second, right? This is simple, huh? Okay? You don't need an inner product. You just count this. Huh? This is what they call the natural action of a covector on a vector, all right? Normally, when you do that, you use inner products and all this junk, but it's not necessary here, all right? You see that? That's how you would do it. That's how you would do it on it. Huh? The way they calculate, so this is what they call the pairing. So you take a price and you pair it with your quantity demanded, and we'll give you a number too in dollars per year I had here. Okay, but these are not money dollars. These are valuation dollars I have here. It's just that I have the dollar sign really close on my keyboard. So in the euro I have to type something complicated. All right? And then fancy guy, if you do differential geometry, they'll also use this hook here. So you have this price and you're hooking this velocity, it's like you hook it in there and you also get 2. It's just notation, You look a little worried. Huh?
I'm trying to think, how does this alpha look like?
Well, this alpha is just now this thing.
Yeah, I know, but...
now, we'll go back to coordinates. Yeah, that's the next slide we're gonna, yeah? So I first want you to see that you can do it purely without any coordinates, without any inner products, nothing. You just, and that's how you would do it if you would look at that map, right? You say, woo, count the number, right? So what I want to do is bring you back to this, the simple coordinate-free kind of thinking. What's really physically going on here? Okay, in this case, not physically, but economically, right? You can just eyeball this. That means it's not going to depend on how you chose coordinates, how you measure this price gradient or all of this, right? So it is. I call it the price gradient because it's the gradient. It's just the gradient of that mountain. I could have called it the benefit gradient or the cost gradient, but you'll find out why I'm calling it the price gradient. Okay? And the quantity demanded is this flow. It is like a vector, It's like how fast you're flowing over these mountains. You're walking, it's your speed. And these things, they work together. It's a little bit the same as a current and a voltage, right? So the voltage is actually a gradient. So you actually, when you have a voltage, you give these two terminals, and then you plot it like this, and then now you have some vector, or there's the current, and it goes over this voltage, and you accumulate power, right? Okay, this is the same mechanism that's going on here, but that will all become clearer. Okay. Yeah, so you're worried about the right thing, but it will come. I first want, so you can already see how good a description this is. So suppose the mountain is steep, right? Then you'll have a situation like this, and the result will be 4, right? Rather than 2. But prices are steep too, right? The price level, we talk about a price level, here's a level. I mean, the price is steep, okay? The price can be gentle, okay? So that's when the slope is gentle, right? So you see, the idea that a price is a gradient is built into our language. That's what you got to see. You can also say a price is high, but that's the same thing what you mean. You see, the price is not big. That's kind of bad English, okay? What's the size, good English is the price is high, but the demand is big, the quantity you're demanding, that's large, all right? Okay? There's a lot of stuff you're demanding, but it's not a lot of price. You know, that's nonsense. All right, it's high. So this highness level, those are covectors, and the intensity, the size, the quantity demanded, those are always vectors, right? Okay. Huh? So this is there to show you how natural this feeling is, because we use the words. So, all right. And this one is when it's 1. So here you get 1. This is what we call a nominal pricing, right? So you price things at 1. So sometimes money is priced at this, right? So this is a flow of money, and then this will be the value, and then you say this is nominal. But real values, then all of a sudden you'll see that the money gets worth less or more, you know, usually less. Huh? And, you know, then the value of the money has to be measured by this. Huh? But at nominal, you set it equal to 1 at some point, okay? Or sometimes at par, you would call this at par. Huh? Huh? So par means even. Huh? Pair in French, ampere. Huh? So that the length of your vector is equal to the distance or the height accumulated. So they're even. Huh? Even means, you know, you come out the same. Odd is when you're off. Okay? So this is how you would do this if you don't have any coordinates, okay? Now, Andre is already worrying, how does this work out? He was already trying to do it, and you probably resolved it, because it's not so hard. So the thing is, suppose you have this inventory and report and this price list, then you can look at this thing, you can look at the components of this thing, right? Huh? Because you know this is Q1, this is Q2, so this one will have 2 components. It will be P1 and P2, right? Huh? So this one will only have P2, and this one will only have P1, right? Huh? This is only in the, so this one will be P1, you know, DQ1, and the other one is in the other direction. All right? Huh? Okay? So you can write it out in components. So here I wrote it out in components. This is just the different price components. So you have, you know, D goods and N, big N agents, so N degrees of freedom, each one over a price. Okay? Huh? Here there are 2. All right? Then what you can do is to calculate, then this vector, this is the vector, and this is this one form. Huh? So this vector has in the q direction, this vector has a rate q dot, and in the q direction, the q level direction, it has a price p. Okay? This alpha. That's the component of the price gradient. Okay? That's what we're going to call P. That's a number, okay? Just like Q dot is the component of this vector, okay? Then if I do the same trick, I calculate, you'll see that if you that eyeballing of yours basically is doing this, okay? And this is just your regular old inner product. Or if you look at this as a row vector and you make Q dot a column vector, Q dot 1, Q dot 2, then you can see this is a matrix product, right? So the covector is on a row and the vector will be a regular column, all right? That's probably the nicest way to see it. Huh? Otherwise, you have to turn this row vector into a column vector by taking the transpose, and then you have to take the inner product. That's just even messier, okay? Okay? This is how this works.
But if we have arbitrary directions in the, and there's separate spaces, in all the spaces we have arbitrary charts,
Yeah.
We can draw an arbitrary chart. Then how do you know, maybe this is a stupid question, how do you know that the components correspond to each other? Like because we use the index 1 and we say, yeah, P1, Q1, Q dot 1.
Yeah.
But I mean, it could be like,
I know, but that's
also not in the same geometrical space, like it's a separate thing, this covector.
yeah, that's the magic, right?
So how do you know?
That's the magic because of this setup. All right, there's a couple of things you're going to find out. But because of this setup, you'll realize that this is coordinate free. So if you choose coordinates, different type of coordinates, nothing will happen. It's just the same thing, but then in different coordinates. So if you had a momentum and a velocity, you try to look at the interaction between the two, or a force and a velocity. It doesn't matter. Force is also a covector, right? Because, then you're going to look at it in a different coordinate system, rotational coordinates, angular coordinates. It's not going to make a difference if you did the thing right, okay? Now what happens is, this is exactly why a vector, this is one that's called, I always forget, this one is called covariant, and this one contravariant, I believe. And it really doesn't matter. If one is contravariant, so when you vary this one varies in the other way to compensate for it. So when you rescale, so suppose you have this thing here, and then, I mean, this is a good question. It just happens to have a good answer. And then suppose you have this vector, right? And then I have some coordinate frame here, right? Now suppose I boost this up in both directions, you know? What's going to happen? Now this vector will become twice as long, right? For instance. And well, this thing have to also become, this will, you know, twice as big. So this thing will go over here, right? That's it. To keep the thing straight. Okay? So they vary along with each other. Okay?
So basically you can't get it, well, you can't get it wrong. Like,
No!
it's just it's a, like, what you call, like, the natural pairing is just the way.
Yeah, that's because it's a natural pairing. And why is it called a natural pairing? Because it is natural, meaning you don't need coordinates. That's what I try to do here, right? You call something natural if it just follows nature, right? So people say natural pairing, but sometimes they don't mean anything natural about it. But this one is really natural. I just followed nature. I did this whole calculation without bringing in coordinates. Now then you later bring in the coordinates, okay, whoopity-doo. You can do whatever you like. You know? That's not going to change because this thing may change. This thing may change. Your row vector may change. Your column vector may change. But the pairing, the product has got to be the same. I mean, you know, you can take rotational coordinates, or you can hyperbolic coordinates. You can do crazy coordinates. Now, if they're different, you know who is in error, not nature, you. You see? Okay? So you screwed up something in your coordinates charting. Okay? So same with power. Look, at a certain point, this is your force. It's just this vector. And this is what you have to overcome. This is the, well, the force, it will be a covector. And then this is how you displace. This is a vector. And then if you then measure displacement another way, then you've got to adjust the force too, because that's per unit of displacement, right? That's all. And then you rotate, then you got to rotate everything along. Now, the way they do is it can get complicated. So sometimes, like in the plane, you can just move things around or rotate. But if you're on SO3, you can't. It's very complicated how you move one and how to move the other, right? So on the Earth already, you see the problem. So how do you move a vector? You have to go like that. But how do you move a covector? That also has to move along, you know, to keep everything. So you do all these complicated coordinate transformations, but that's what you do in mechanics, like T and B coordinates, you know. And what else do you have, you know, all kinds of coordinates. You remember the T and B coordinates, Tangent, normal, whatever. Yeah, you know. Yeah, so I remember teaching that class. We had to teach you all these different coordinate systems. But did that change the outcome? No. You'll know, If it did, you screwed up in your,
Also, if you like start with multiple charts, because they are open, and you cover the manifold, you always have these overlapping sections in your charts. And then if you look at these overlapping sections, then you can say, okay, maybe I can define a smooth function that maps my coordinates in one to another. And you know that these are going to exist. It's called the partition of unity. And then you know that, oh, actually we can just first do the geometry and then put some coordinates on.
Okay.
Yeah.
Yeah.
Cool.
Yeah.
Convenient. Reality.
Well, it's more than just convenience. It's like you have no, it's just, yeah, it is convenient, but I think what's deeper is you got to see that this whole analysis is just, nature doesn't care about your coordinates, okay? And that's what's wrong with these guys who immediately have coordinate systems. Then you can't unravel anymore what's a special part of your coordinate system and whether you chose that right or whether it works, So you have the Earth. You have a map. Okay, great, you have a map of the Earth. And then what? I mean, then you can say, well, I'm using my Carter map, so now the distances are really, look, dude, huh? You put your legend there and, huh? And then you can say what he says, well, how do I know what happens on the North Pole? Well, you got to get a different map, and then at a certain point, you got to go from one to the other, and there's going to be some overlap, where the map stereographic from the North Pole overlaps with your Mercator map, and you got to be careful that you get the legends, lined up and everything lined up, But the Earth doesn't really care about what mapping you used, huh? That's the thing. It's just you pressing this thing in flat space. Now, how can any law of nature depend on this? How can this ever go wrong? You see, because the nature doesn't care about it. So the laws of nature have to be invariant under these allowable transformation. They can't depend on it, you see. So a lot of laws, before they had this, there were all these supposed laws, and you see it a lot of economics, but they totally depend on how you choose, what coordinates you chose, right? Totally. And how is that useful, Huh? You see? It's just going to screw everything up. It can't, huh? So things are called unphysical if they depend on the coordinate system. So there were some laws that people find, but you can have AI find a law for you, but if it depends on how you chose your coordinate system, it's a ridiculous thing. I mean, maybe it holds for a little bit, but it's going to fall apart. Huh? It's got to. Okay? So, I actually I had some more stuff, but I think we're running out of time. Huh? I think this is enough, huh? Because it takes a while to process this. All right? But the message is, develop a coordinate-free intuition and then bring in the coordinates when you have to. But, huh? Okay. Now, of course, when you guys learn this material mechanics, everybody has already fallen in all the pitfalls. So they'll make sure that, this is all right, and then you learn how to deal with these things. But here it's different. We don't know yet what coordinates we want to choose. We do that, and it's really useful to, huh? Okay? Okay. Now, then we'll finish this off next time. And by the way, there'll be a half hour. The room is booked in some emergency until 4:30. Huh? So we'll start half an hour later. All right? I'll send this also in the invite.
Listen.